All right, welcome back to Finite Element Methods, Math 574 here at the University of Tennessee. This is class number 2. Today we're going to be talking about the fundamental Galerkin orthogonality, Say's lemma, stiffness matrix, and Hilbert spaces. So we talked a bit about um, uh, the model problem last time and the weak formulation for the model problem, that Poisson type problem. We talked about the standard Galerkin approach to approximating solutions to that, and then we talked about a Galerkin type of optimization approach for also getting approximate solutions, which turned out to be analogous or equivalent to the Galerkin approach. And so that was called the Ritz-Galerkin approach. And now we want to talk about how we can get estimates for the approximations that we're making. And the fundamental Galerkin orthogonality and Say's lemma play an important role in that. So suppose that U in V solves 1.6. So 1.6 was the weak formulation of the problem, and 1.9 was the Galerkin approximation of that using that weak form. Remember, the Galerkin approximation was you're looking for a solution which is now in a finite dimensional subspace, which has a particular basis associated to it. Well, any finite dimensional subspace does, but um, we have a perfect or a standard. Maybe I haven't even gotten to that yet, but we have a standard way of writing that basis, which we'll get to momentarily. If these two functions satisfy these two problems, then their difference when, how can I say it? When I put in the difference here in this A bilinear form, it doesn't matter first or second location because it's a symmetric form, and we test it against this an arbitrary function V from VH, then I find that that inner product or that bilinear form works out to be 0. We're going to find out later that this is an inner product, so I may make a mistake from time to time and just immediately refer to it as an inner product. Right now, we're just calling it the energy bilinear form or the bilinear form of the problem. So this is what we call the fundamental Galerkin orthogonality. If I take two vectors and I put them into an inner product and I find that when I test the one with the other in the inner product, I get 0, then we call those two vectors orthogonal. So essentially this vector and this vector are orthogonal in this metric. This identity, 2.1, is called the fundamental Galerkin orthogonality, FGO. And so let's see how we prove this. So because F solves 1.6, we can write this. But now this is true for every V in the space capital V. But VH is a subspace of V. So what do we do in that case? Well, that means that I can replace this test function by restricting it to this smaller set. So for example, it must be true that this is satisfied for every V in VH as well, because VH is a subspace, actually a subset, but a subspace of V. Okay, so that's one thing we're going to put in our pocket. The next thing I want to put in my pocket is the fact that we know that UH solves 1.9. This is the Galerkin approximation. So as the solution of the Galerkin approximation, it satisfies this equation for all V and VH. And now all I'm going to do is subtract these two equations, subtract this from that, and use the linearity of the A bilinear form in the first entry. If I do that, then I get that. But as I'm subtracting this from that, I just get 0. And so that's the fundamental Galerkin orthogonality. It's very quick and very short. Now, I haven't proven yet that solutions to 1.6 and 1.9 are even available. I can't guarantee that they exist, can't guarantee that they're unique yet. Or I may be able to do that, but I haven't demonstrated those properties yet. So we'll come back to that. The question of the existence and uniqueness of these solutions is still up in the air. We'll give a partial answer to the existence and uniqueness question a little bit later on, because we can show that 1.9 actually has a solution, whether or not we know 1.6 has a solution or not. Using the fundamental Galerkin orthogonality, we can prove something called Say's lemma. So what is Say's lemma? So Say's lemma is a kind of best approximation result, and it uses this fundamental Galerkin orthogonality. And in fact, I can show you a picture which kind of demonstrates both the fundamental Galerkin orthogonality and Say's lemma in one nice graphic, and we'll do that in a little bit. So what this best approximation of property says is that if U solves the original PDE, this is the weak form of the PDE, and UH is its Galerkin approximation, then their difference, when measured in the energy norm, is exactly equal to the infimum. So this is the smallest, that is the smallest that this can be made. This object here, remember this is fixed. This is my solution to the weak form of the PDE. So this is equal to the smallest it can possibly be by taking this second element here in U minus V from anything in V, VH. So when I minimize this over V and VH, then I get this number. So this, right, this is a number. Of course, the norms are numbers. I really can't make, so I hope everyone knows what an infimum and supremum are. Infimum is like the minimum, okay? Not exactly the same characteristics as the minimum. Um, it's also called the greatest lower bound, the GLB, greatest lower bound. That's the English version of it, and I think that has a little bit rings a little bit more. Well, it's more instructive, that name. And the supremum, the counterpart of the infimum, is like the least upper bound, and sometimes the least upper bound is represented as LUB, and the infimum is by GLB, the greatest lower bound, the lub and the glub. But we're going to use the French versions, infimum and supremum, because they're much more standard in the literature, I think, nowadays. Okay, so this is as small as that can be. This makes it as small as it can be in this norm, E. So how do we prove this? The easiest way to prove it is to use the definition of the energy norm. If I square that, I'm just going to get the energy inner product, or the energy bilinear form, of this object in here against itself. Remember, the way it's defined is by or via a square root. So the next thing I'm going to do is expand this. Well, not expand it yet. I'm going to actually add 0. I'm going to add 0. I'm going to let V in VH be anything. Let it be arbitrary. So if I do that, then what do I get? I'm now going to use the linearity of the bilinear form A in its second component. So the first component stays the same. What do I get with the second component? Well, what do I get with the first component? I'm going to bring these two things together, U minus V, and what's left over is V minus UH. But that is in VH because of my assumption that V is an arbitrary object in VH. UH is certainly in VH. V is in VH, and this is a subspace. So subspace means that if I add anything to something else in the subspace, I get something in the subspace. So it stays in the subspace. So now my fundamental Galerkin orthogonality says that that has to be exactly equal to 0. So that's why that term disappears, and I'm only left with that term. Now I'm going to take the Cauchy-Schwarz inequality. Remember, this is simply I mean, we're going to show that it's an inner product, so this really does follow from the standard Cauchy-Schwarz. But really, I'm applying Cauchy-Schwarz for the object that we have here, which was an integral. Remember how A was defined? A u v was defined as the integral u v dx. Okay, so really, oops, I should put, it's really the gradient of u dotted with the gradient of v. So I can apply Cauchy-Schwarz as I would to normal integral. Okay, and that's what I mean when I'm applying Cauchy-Schwarz here. So after the application of Cauchy-Schwarz, I get this. Now, as long as u is not equal to uh, then I can use the cancellation property, divide both sides by this positive number, if u is not equal to uh, cancel one power of that and that term there, and then I'm left with that inequality. But notice that v was absolutely arbitrary, so this inequality holds for all v and vh without any specification of what v I'm choosing. And all I have to do is assume that u is not equal to uh. Now, if u equals that's a trivial case, which I'll allow you to check on your own. You'll see that the thing above is satisfied uniquely without, or satisfies trivially, the thing that we're trying to prove. So we're not losing any generality by assuming this. Now, this, okay, is kind of a set of numbers. If I change v, I get another number. If I change v still, I get another number. Now, this is independent of v. So the fact that this holds for all v means that if I take the infimum over all such numbers, of course, we know that that forms a set of non-negative numbers. And it turns out actually to be a positive number, a set of positive numbers. If I take the infimum over all v and vh, then I naturally have this being greater than this lower bound. So this is a lower bound for all of these numbers. Now, this is where the English, I think, serves a little bit better than the French term. So what is the infimum? It is the greatest lower bound. Okay, the greatest lower bound. Well, the infimum has to be bigger than any other lower bound. So this is a lower bound on numbers like this, and the infimum is the greatest lower bound, so it has to sit above that. That's how I justify that. But now look at this. If I take a particular object out of VH and put it in there, I should get something bigger than the infimum. Do you agree? So if I take the particular object, which happens to be UH, it has to be bigger than the number generated by the infimum, because the infimum is the greatest lower bound. This is just any other number. But now I have looks like a seeming contradiction, but it's not a contradiction exactly, because it is possible that all three of these things equal to each other. Well, these two have to equal each other, and that forces this, kind of like the squeeze theorem, to be exactly equal to that. The only way that this can happen, in fact, is if I have that u minus UH in the energy norm is equal to the infimum of u minus V taken over all possible V and VH. So that's what we call Say's lemma, and it's a best approximation. We're going to use that later on to derive error estimates for the finite element method. That's going to be kind of the fundamental step in proving error estimates in the finite element setting. So here's the picture of the fundamental Galerkin orthogonality. I'm kind of pretending here that my bilinear form is something like the Euclidean inner product. It isn't. This is just a kind of cartoon. But so we have these two spaces. V is the parent space, and VH is the subspace. Subspace has to go through 0, so here's my origin 0. And now U is any vector or any point in V. It solves the true, it solves the weak form of the PDE. And what is UH? UH is the Galerkin approximation. So this difference should be orthogonal to any V that is in VH. So maybe I'll remove that H from that. There we go. Does that make sense? So here's that. If you want to think about things in terms of Euclidean things, I can pick up this vector and put it here, and it's clearly orthogonal to that difference vector, right? So that difference vector would be U minus UH would be pointed that way, and V would be pointed that way, and they're orthogonal. This is the picture. This is the picture. VH is a subspace. Now, why is this the best approximation? Why is this the best approximation? Press the wrong button there. Why is that the best approximation to that? Well, it's kind of the closest that you can get to it, right, in the Euclidean sense. But the fact that it's orthogonal in this inner product means that this distance here is made as small as possible if I measure in the right metric. Okay, so this is a kind of topological kind of, well, not really topological, I guess. It's a kind of inner product space argument of why this best approximation, how and why it occurs. So now the next question is my Galerkin approximation to this model problem, is it computable? What does it look like? So to do that, what we're going to do to answer that question, let's use a particular basis for our finite dimensional subspace, and let's convert our Galerkin approximation into a matrix problem that we can analyze a little bit more easily. So suppose that U in VH solves the weak problem. Well, it is actually the Galerkin I'll say, suppose that is the Galerkin approximation. Okay. So U in UH is the Galerkin approximation if and only if UH solves this problem. This is kind of a middle step that I need before I get on to my full construction of this thing called the stiffness matrix and the matrix problem that I want to get to. So I need this intermediate result. U in VH is the Galerkin approximation. That means it solves that. Or, yeah, I mean, that's by definition, right? This is the Galerkin approximation, if and only if it solves this equation, which isn't exactly the Galerkin approximation. Let's peel away some layers here. Right, so this AUH psi I or phi I, f phi I in the L2 norm for all I equals 1 to m, where B is this basis containing these phi functions. So these phi functions are my basis elements. So we're saying that if you have a solution to the Galerkin approximation, it's the same as this function which solves this problem, where instead of putting an arbitrary v in the place of the test function, we put the m basis functions phi I, phi 1, phi 2, phi 3, up to phi m. And vice versa. If I know that I have, or I solve this problem, where for test functions I have just the basis functions, then this UH is the original Galerkin approximation that we defined. I think previously we called that 1.9. Okay, so let's see if we can prove this. Well, the first direction is rather easy. If we know that UH solves 2.3, then we could just, instead of considering an arbitrary vector there, we could just put in one of the m basis functions phi I. In fact, we could put in all of them in turn. But if I put in all of them in turn into this position, then that means I've satisfied that problem. Since this is a pretty powerful statement, it holds for all, and we only really want to put in m of those, going in this direction is pretty straightforward. What about going in the other direction? So if we start with this fact, can we show that UH is actually the Galerkin approximation, which solves that? I wouldn't say it if it wasn't true. It is true. Suppose that UH solves 2.4. 2.4 is this equation where we've used, for the test functions, just the basis functions. And we're going to let V in VH be arbitrary. If it's arbitrary, then there exists unique, I should say, that's my symbol for exists unique, exists bang, exists unique. There exists unique Ci in R, I equals 1 to m, such that V is equal to that basis expansion. So this is just a way of saying every V has a unique, every function has a unique basis expansion. So let's write that there. Unique basis expansion. Okay. We always have unique basis expansions in finite dimensions, right? So now I want to show ultimately that this is equal to that. And since V is arbitrary, I'll be done. But this is easy to do. So write for this guy, it's a basis expansion. Use the linearity of A in its second component. We pull out the sum and the coefficient Ci. We know that this is equal to that by our assumption 2.4. So let's write that. 2.4 is used there. Okay, now we can bring the sum and these coefficients back inside because the L2 inner product is also a bilinear form. It's linear in its second component. And then finally, we recognize this reassembles as just V. And so we get f of V. So now since V is arbitrary, we're done. We've shown that that's the Galerkin approximation. All right, so Galerkin approximation is equivalent to this problem here. And it doesn't matter what basis you use as long as you use some basis for your finite element space or whatever space you're using, your finite dimensional space. We're going to use a finite element basis because this is a course on finite elements. And what else would we use? Suppose that B is a basis for VH. The matrix, so this is my notation for matrix. Usually I'm going to use a capital A a capital letter, I should say. Some people will put a little twiddle under that since on the blackboard is a little bit hard to use different fonts, but capital letters generally. And then the lowercase Roman letter associated to that is going to represent the components, but I have to put subscripts on the components because they're usually indexed. So a matrix is a two-dimensional array, gets two indices or a two tensor. And those indices run from 1 to m, both of them. ij goes from 1 to m. This is my notation for the set of m by m matrices. And what defines a matrix is what are its components. So I'm going to tell you what are its components or its entries. Its entries are aij, that's what I'm symbolizing there. Aij is equal to a of phi j phi I, for I and j equals 1 to m. Now you may think that I've gotten an error here and permuted these two indices. I have not. This is exactly what I want. However, you should notice that A is a symmetric bilinear form, And so I could push that element there and that element there. It doesn't matter. Based on my definition of this bilinear form, I can put the phi j and the phi I in either position I want. So this matrix is called the stiffness matrix. That's a special matrix, and we're going to use it an awful lot. So we give it a name, and it's called the stiffness matrix. The vector f, so vectors I write with a little arrow above it. It's a little hard to see that arrow, but he's living right above that f. And here's how I write the vector space Rm, who's the space of all vectors of length m with real entries. And this vector is defined by giving its entries. Its entries are just these numbers fi from I equals 1 to m. And precisely fi is equal to f tested against phi I in the L2 inner product. Okay, everyone I hope knows what an L2 inner product is. Okay, so those are the two things I wanted to define, a matrix and a vector. And now one thing you'll recognize right away, and I've already mentioned it, that is that the A matrix is symmetric because it doesn't matter, I can move these entries around. I can change them. So that means that Aij is equal to Aji, right? So that means that A is a symmetric matrix. The stiffness matrix is always symmetric for this model problem because our bilinear form is a symmetric bilinear form. Now, there are going to be finite element problems where the bilinear form is not going to be symmetric. That's okay. We don't have symmetry, but we can still prove a lot of things and we can still do a lot of things. We'll come to that later. Suppose that B is a basis for VH. Now, V doesn't necessarily have a basis because we don't know if it's going to be finite dimensional or not. We only are asserting that VH is finite dimensional. The parent space V could be infinite dimensional, and in general it is for the problems that we want to study. Suppose that A and F are assembled as above. In fact, when we start talking about writing code, we'll talk about assembling the stiffness matrix and the load vector. And see, I gave that a name, right? Yeah, I might have forgotten to say it, but F is called the load vector. We're going to talk about assembling the stiffness matrix and the load vector, and I'll give you actual procedures for doing this. All right, then UH and VH solves the weak problem 2.3, that is the Galerkin approximation. If and only if, and actually I want to write it like that. So I guess I shouldn't say it as. So let's say it like that. Satisfies the Galerkin approximation 2.3 if and only if the vector u, what is the vector u? It's a vector in Rm, solves AU equals F, where u is the vector whose components are the coefficients in the basis expansion for UH. In other words, UH is written in the basis expansion. Remember, it has a unique basis expansion. So I could put the word unique in front of this word coefficients. So just keep that in mind. So U is the vector whose components are the unique coefficients in the basis expansion for UH in VH. Remember, this is a function, not a vector. This is a vector. So in other words, UH is equal to I equals 1 to M, UI, phi I. So here are the coefficients that I want to pick up, and those are precisely going to be that was not very straight, was it? So those are precisely going to go into there and give me the coefficients for this vector I'm going to call U. Another way of writing, if I want to extract, this is a common notation that I'll use. If I want to extract the ith component of a vector, I'm going to put the vector in brackets, square brackets, and I'm going to put a subscript I. That means I'm extracting the ith component of that vector, and so that's the same as ui. So that's my notation here is, this is a common one that I'll use a lot. If I want to extract the ith component, that's just something I'm going to call the ith component. Okay, those mean the same things. All right. So this is an if and only if. We're trying to show that if I solve this problem, then that's equivalent to solving this matrix problem. The Galerkin approximation is a problem that I have to solve. But the way I'm going to do it in the computer and in practice is I'm going to use a matrix vector problem, and I'm going to invert that matrix or use an LU decomposition or another fast solver method to satisfy that or solve that equation. And I had a whole course last semester on multigrid methods, or actually the whole last year, where we talked about that. All right, so let's go and prove this by starting with the assumption that UH in VH satisfies the Galerkin approximation 2.3. So U solves 2.3 means that UH against phi I is equal to F against phi I in the L2 inner product for all I, right? Because I already proved that 3.2 is equivalent to this object here, right? This thing here. And I don't have a name for this, but this is essentially just the Galerkin approximation again. So we just proved that. Now, since H is in VH and B is a basis, then there are unique coefficients, UJ in R, right? They're real numbers. J equals 1 to M, such that UH is equal to that basis expansion. So now I'm just going to set U, I'm going to define U to be equal to those coefficients. So I'm trying to go towards the matrix. Now, we want to show that this matrix is equal to, matrix vector product is equal to a vector. So the way I'm going to do that, and the easiest way to do this, is just to examine the ith component of that vector. A is a matrix, multiply it times U, that's going to be a vector, and I'm going to extract the ith component of that vector and try to show that that's actually equal to the ith component of F. And if that's the case, then I've shown what I want. Well, I'm just going to use the definition of matrix vector multiplication. And in extracting the ith component, there's the ith component exactly there. So this sum contracts in the tensor notation, or the tensor way of saying it. This sum contracts out this jth component, and it leaves only an ith component. So this is actually, you can tell this is these are the components of a vector because it has one free variable. The j, the summation variable, is called a dummy variable because I can replace that with any other variable. Okay. Now I'm going to replace aij with its definition, which is just a of phi j, phi I. Remember, I was really keen on keeping this order. Now the jth dependence, the jth dependence is here, and I want to move this coefficient in here to the first component. Can I do that? Yeah, I can move it into the second component if I want, or the first component, doesn't matter. I'm going to move it into the first component, and I'm simultaneously going to move the sum into the first component because the sum doesn't really act on that. I can reassemble this as the function because that's, was defined as this. Well, it wasn't defined that way. It started out being defined as the Galerkin approximation, right? And we know that it has a unique basis expansion. That's kind of how the vector u was defined. So now I can replace this with but I know that this is equal to that. Okay, so I don't have a number on that equation, so I can't use a number, but it's this one here. So this equals that. But now this is just our definition for the ith component of f. So that means that the ith component of AU equals the ith component of f, and therefore that means that AU equals f. The matrix times the vector u equals the vector f. Now let's suppose that u in Rm solves the matrix problem, and we're not saying whether the solution exists or not yet. We're just saying we're going to suppose that a solution exists. Then we're going to show that that solution has to satisfy the Galerkin approximation. Here's how we're going to do it. So u is a vector. If that solution exists, then it's a vector with m components. We're going to use those m components to construct a function we're going to call We're going to conveniently call it But now all I have to do is run that last computation kind of in reverse, and I can show that this function actually satisfies the equations for the Galerkin approximation, or is, in other words, the Galerkin approximation. And it's not much harder than running that last argument. Not exactly in reverse. That I don't mean you start this way and go up. You kind of have to go in a slightly different fashion, but I'll leave that to you to prove. So it's not hard. So now we've shown that the Galerkin approximation is essentially equivalent to this matrix problem. In other words, if I solve the matrix problem, I have a solution to the Galerkin problem or approximation problem, and if I solve the Galerkin approximation problem, I have a solution to this matrix problem. So we say that their solution sets are equivalent. Now, there might be nothing in those solution sets. There might be an infinite number of things in the solution sets, but whatever's in there has to be in the other solution set. So the solution sets are the same. Now let's answer a basic question. So we know when a matrix problem has a unique solution, especially for a square system like this. So we know that it has a unique solution, in this case, if A is an invertible matrix. Let's give a very simple proof that this is true. The stiffness matrix, as we've computed it above, is a square matrix, of course. And it turns out that it's also a symmetric positive definite matrix. So this is my notation for symmetric positive definite, SPD, symmetric positive definite. Okay. I'm assuming you've seen that abbreviation before, but if you haven't, maybe write it down. Symmetric positive definite, SPD. We've already addressed one part of what it means to be symmetric positive definite. A is clearly symmetric. So that takes care of one part. Now, for the next part, let's assume that V is an arbitrary vector in Rm, but well, we don't want the zero vector, so let's exclude that for kind of obvious reasons. So suppose it's arbitrary but not zero, and then let's calculate this. This is what's called a quadratic form. Let's calculate this quadratic form and see what we get. Well, we know we know how to do this for matrices and vectors, right? So this will end up being a double sum over I and j, vi, aij, vj. So if you can't see that right away, maybe compute the components of this guy and then take the dot product of the two. This sum is coming because of the dot product. This sum here is coming because of this matrix vector product. Now we replace Aij with its definition. Simultaneously, we pull in the sum and these two numbers. These are just end up being numbers or coefficients. Okay, use the definition. Pull in the sum and these coefficients, sum and coefficient, and then we're going to reassemble these objects here and here, and we're going to notice that that's just the same thing. It's just going to be v twice, where v is equal to this function. So we know that it has to be a function in VH because it's a basis, or it's expanded in the basis of VH, and VH is a vector space. So what does this say? This is equal to that. But remember, we said before that this is equal to our energy norm squared. So this was something we discussed last time. And we made a brief point about this, but we'll get more into this and get into more detail in a little bit. This is actually going to prove to be a norm. So if v is not equal to 0 in the space, then we know that this function, or this norm, has to be strictly greater than 0. Okay? We'll talk about that in a lot of detail coming up. We're not going to leave that as a loose end for very long. But for right now, it is a loose end. The fact that this is not 0, not the 0 function, means that this norm, or its square, doesn't matter, norm or norm square, is strictly positive. This means that A is symmetric positive definite, because this is always greater than 0 as long as V is not equal to 0, but V is not equal to 0 as long as the V transpose, or sorry, as long as the vector V is not equal to 0. Okay, so maybe one more minor little step there. Remember, to be positive definite, you want this form, this quadratic form, to always be positive for any v which is not equal to 0. Always positive for any v which is not equal to 0. And it is that case. So we're done. A is symmetric positive definite. Now this says something really powerful. This says that our problem 2.3, which we can go all the way back to, has a unique solution. Why? Well, this follows because A is symmetric positive definite. And that means that the matrix problem AU equals F has a unique solution. But if AU equals F has a unique solution, that means that the Galerkin approximation 2.3 has to have a unique solution. And therefore, we're completely done. So that's a nice little corollary, right? It tells us that the Galerkin approximation always exists and is unique. It doesn't tell us whether our initial weak formulation to the Poisson problem has a unique solution or not. That is still an open question as far as we're concerned. And to answer that question, we need to talk a bit about something called Hilbert space. So we need a little bit of a discussion of functional analysis, because functional analysis is where the theory of finite element method is kind of written. So we won't get to what is a functional and why it's called functional analysis in this particular class, but we're going to head in that direction. We first need to know, for functional analysis, pretty important to know what we mean by inner products, what we mean by norms, what we mean by convergence, completeness, things like that. So let V be a linear space. I'm going to use the term linear space or vector space. It doesn't matter. Sometimes it's better to use the term linear space, because vectors, a lot of people view vectors as arrows in R2 or R3. But that's not what I mean when I say vector here. I mean something a little bit more general and generic. So I'll try to use the term linear space, but I might fumble and call it a vector space. And we're going to think about vector spaces entirely over R, not over complex numbers or any other field. An inner product is a function that takes two vectors or elements or points from the vector space, linear space, and it combines them together and produces a real number in return. And it's a function with the following properties. For all v and v, remember now v is just a generic vector space. For all v and v, v against v, sometimes I'll say v tested against v or v against itself is strictly or is greater than or equal to 0, and v tested against itself is equal to 0 if and only if v is equal to the 0 vector in the space, or the 0 function or whatever I'm talking about in that space, the 0 point. That's what we call the positivity property. Now, the Euclidean inner product, for example, has that property. So a good thing to think about is the Euclidean inner product, right? So that's the same as the dot product. Okay, every inner product also has to be symmetric, or it has to have the symmetry property. For all u and v and v, uv is equal to vu, okay? Or u tested against v is the same as v tested against u. The positioning doesn't matter for an inner product. And finally, it has to be linear. Now, I only have to express the linearity in the first component because the symmetry guarantees that linearity will also happen for the second component as well. For all u, v, w in space, and every scalar alpha and beta, alpha u plus beta v tested against w is equal to alpha u tested against w plus beta v tested against w. Okay, so it's linear in the first component, but of course by symmetry it has to be linear in the second component as well, because I can flip the two things around. I don't have to re-express that. That's an added assumption that I don't need. I don't need to say it's linear in the second component, only in the first. Or the second, doesn't matter. Let V be a linear space over R, then a norm is another kind of function with the following properties. Now, a norm only takes a vector, not a pair of vectors. It takes one vector and maps it into the real numbers. Now, not all real numbers. It only takes these vectors and maps them into the non-negative real numbers, 0 and positive reals. That's because of the positivity property that's first, which says that for all v and v, the norm of v is greater than or equal to 0. So it's a non-negative real number, and it has this positivity property which says that the only way the norm can be equal to 0 is if the function or object was 0 to begin with. Okay, so that's a positivity property. The next property of a norm is what we call the non-negative homogeneity property. And that says that alpha times v in the norm is equal to the absolute value. Now, if I was over the complex fields, this would be the modulus, but we're in real land. So this is absolute value times the norm of v. So non-negative homogeneity means if this was a non-negative number, then it would come out as itself. Okay. That holds for all alpha in R and all v in v. And finally, we have the triangularity property, or the triangle inequality property. And that says that for all v and u in v, U plus V in norm is less than the norm of U plus the norm of V. Okay. Standard triangle inequality property, what I'm calling called the triangularity property, which isn't quite right, but I decided to call it that anyway. So a linear space V with an inner product is called an inner product space, and one with a norm is called a normed linear space. Now I usually, I'm going to do that here and below. If I want to be specific about what inner product I have associated with that space, then I'll put the inner product second. So if I want to specify an inner product space and say which inner product I'm using, I use this notation. Because some spaces are inner products when you pair them, inner product spaces when you pair them with one bilinear form and not with another, or they change their structure when you change inner products. So, for example, I might have a space which is complete with respect to one inner product, but not complete with respect to another inner product. Um, right. Uh, so let's suppose or consider an inner product space. Then for all U and V in V, this inequality holds. This is exactly the same as the inequality we established um, in the last lecture. And we gave it another name there. In fact, we called it we called these just the norms, and we're going to see why that's possible to do so. But this is just the Cauchy-Schwarz uh, the Cauchy-Schwarz inequality. Okay, this you can see is a norm, and this is a norm, and of course I'm going to emphasize that when I make a definition below. So equality holds if and only if U and V are linearly dependent, and I proved last time why this is the case. So you can go back to lecture 1 and have a look at that, see what we proved there. So the proof is exactly analogous. Now let V be an inner product space, then this object, V equals the square root of V tested against itself, defines a norm. I can show that all the properties of a norm are satisfied. Positivity, non-negative homogeneity, those are easy properties. Positivity, non-negative homogeneity. The only hard one is the triangle inequality. The triangle inequality simply uses the Cauchy-Schwarz inequality when I realize I can replace this now by norm of U and this by norm of V. Therefore, if that's the case, and I'll leave it to you to check those, if it satisfies all the properties of a norm, then that means that I have every inner product space is a normed linear space. Every inner product space is a normed linear space. Okay. Right. So again, this is not hard to prove. There are 3 things I need to check. The axioms for norm, essentially, the positivity, non-negative homogeneity, and the triangularity property. But the last one is the only difficult one, but if you simply apply the Cauchy-Schwarz inequality, then you get it right away. Okay, fine. So now, when we're talking about Hilbert spaces, there's a big concept in Hilbert spaces and what are called Banach spaces as well. And that's the idea of convergence, and probably more so the idea of what's called completeness. And therefore, we need to define what we mean by a sequence converging in the space. And also, we need to know how to define what we mean when we say that a sequence is Cauchy in the space. So all we need to define convergence and Cauchiness and another concept called boundedness is a norm on the space. We don't need the inner product on the space. So that's where we're going to be working from. So suppose that we have a normed linear space. V is the space. This is our norm. A sequence. So my notation for sequence is these are curly brackets here, even though they don't look like it. Every sequence has a subscript. Okay, subscript indicates that's kind of the input, right? So if I put in n equals 1, that gives me the first element of the sequence. N equals 2 gives me the second element. Really, all a sequence is a function over the natural numbers. It's a function over the natural numbers. It's a real valued function over natural numbers. Okay, so this sequence, well, actually not in this case. This sequence is not a real valued function. It's a function over the natural numbers whose elements are in V, whatever that is. Could be a vector. Could be a vector space. It could be a function space, something like that. We say that that sequence converges in V if and only if there is a point V in capital V such that for every epsilon greater than 0, there exists an N such that if N is bigger than capital N, this is my symbol for natural numbers. If N is bigger than that capital N in the natural numbers, then Vn minus V in the norm is less than epsilon. And if this happens, right, so for every epsilon there has to be an N, then we write that Vn converges to Vn converges to V in the space V. And we'll also write, and sometimes just so you know that it's a strong convergence, because we're going to come up with something called a weak convergence. I sometimes put an N above. Sometimes I'll also tag on N goes to infinity below, etc. The same thing is going to be meant by this symbol. Okay, this means exactly the same thing. Okay, if the norm of these differences converge, this is also a kind of sequence. But in fact, it is a sequence, but it's a sequence of positive, non-negative real numbers. And if that sequence converges to 0, then I can show that this all holds. Okay, so this is another way of writing this convergence. So that's what we mean by convergence. The second thing we want to define is what we mean by a Cauchy sequence. So you've all seen this as well before. Vn sequence is called Cauchy if and only if for every epsilon there exists a capital N in the natural numbers. And of course, N depends on epsilon. That's how you should view it. Such that whenever N and M are bigger than capital N, then the difference between Vn and Vm is less than epsilon when measured in the norm. A sequence, right? So a Cauchy sequence is different than a convergent sequence because this entry here is Vm rather than V. See the difference there. A sequence is called bounded if and only if there exists an M, which is a non-negative number, such that for all n in the natural numbers, Vn measured in the norm is always less than M. So this is a little bit like if you're familiar with Euclidean norm and you like to think about that, then this says that all of the elements of the sequence stay in a ball of radius M. Same thing. They all have to stay in a ball, okay, of radius M. So that's what we mean by bounded. All right, now we can easily go in one direction, but not so easily in the other direction. What I mean by that is, so if a sequence is convergent, then it's going to turn out to always be Cauchy. But I'm getting a little bit ahead of myself. Suppose that V is a normed linear space, and suppose we have a convergent sequence. So this is a powerful statement. Suppose we have a convergent sequence. Then Vn is also a bounded sequence. Every convergent sequence has to be a bounded sequence. That makes sense. because um, if I'm converging to something, then I'm probably staying near to that limit point after a certain amount. But for the first few values of my sequence, those also have to be bounded. Okay, so it's pretty easy to see how you can prove that a sequence that is convergent is also bounded. Now, if a sequence converges to two different limit points, let's say V and W, then those two limit points have to be equal. In other words, limit points have to be unique. Limit points have to be unique. And finally, if I have a convergent sequence, then that sequence has to be a Cauchy sequence. So these are all kind of elementary exercises that you've seen probably in your 447 class. And so I won't redo them. We'll finish, I believe we're finishing, yes. We'll finish with a definition and why these things are important. Now, it turns out that if I have a space and I have a Cauchy sequence in that space, that normed linear space, then that Cauchy sequence may or may not converge. There might or might not be a point to which it converges. So an easy example of this is if I take the rational numbers, and I take the well, let's see, is that I'm trying to think, that's not going to be a space, is it? Well, I have to take the rational numbers and I have to use the field of the rational numbers. So it's not exactly going to work. But in any case, I can construct, well, yeah, it works. So if I have a Cauchy sequence consisting of all of the rational numbers, let's say, converging to the square root of 2, but bigger than square root of 2, then this limit, okay, this thing is well defined, right? So if let's say I have a sequence which is converging to the square root of 2, but all of the elements of the sequence are rational numbers. I can do this, right? And suppose that it's a decreasing or increasing sequence of rational numbers. You could just add more digits of the square root of 2. Well, the sequence of rational numbers, of course, is converging to an irrational number. And so if I consider this to be a convergent sequence, then, or a Cauchy sequence, I can show it's Cauchy pretty easily, but it won't be convergent because the square root of 2 doesn't exist in that space. It's not a rational number. Okay, so this is a pretty bad example. There are much more exotic and interesting examples, which we'll get into when we start talking more about functional analysis. And we're not going to do too much functional analysis. We'll talk about functional analysis to the extent we need to, because we're not going to talk about theorems and theory we don't use. We're only going to be interested in the utility of that insofar as it is useful to us. But in any case, not all Cauchy sequences are convergent sequences. A linear space for which every Cauchy sequence, however, is convergent is called a complete space. A linear space for which every Cauchy sequence is convergent is called a complete linear space. And a complete normed linear space is what we call a Banach space. A complete inner product space is what we call a Hilbert space. Okay, so you see the difference. A Hilbert space is actually a Banach space, but a Banach space is not necessarily a Hilbert space. A Hilbert space is a Banach space because remember we said that if you have an inner product, then you have a norm. So a Hilbert space being a complete inner product space means it's also a complete normed linear space. It's also a Banach space, therefore. But a Banach space only has a norm and it doesn't necessarily have an inner product associated to it. So I can't go the other way. So a Hilbert space is a Banach space. A Banach space is not necessarily a Hilbert space. And that's because the Banach space usually is lacking in an inner product. Sometimes you can add them, and sometimes you can add them in such ways they'll be equivalent to the norm. And so sometimes you can't. So be careful about that. All right, so I'm out of lecture notes after 11 pages. It looks like a standard lecture is going to be about 12 of these pages, so that's good to know. But in any case, we're done with the material, and so that's where we'll finish for today.